to talk about. So last time we did talk about some elements of the presentation in the book, particularly sort of type-safe return values. We noted some of the problems with exceptions, the high overhead associated with them, the lack of referential transparency, the fact that they sort of pop you out in terms of the control flow, in terms of how the system sort of works. They pop you out at one point and put you at a higher level where it's hard to often resume what you were doing. Like if you're in the middle of a pipeline, you sort of pop out and you got to get back to the pipeline. It's hard to reason about often, and it's hard to compose them into higher order functions. Like if you have a function that takes another function as an argument, like that integrator, how could you expect the function that takes that other function as an argument to know about all the possible exceptions that function could throw that it's taking as an argument, to be specialized to deal with all of these? It's hard. And you know, exceptions were created a couple decades ago now. I remember, you know, doing C programming where we only accrued approximations to exceptions with something called set jump and long jump, and it was horrible because you'd have memory leaks and so on. And the truth is that exceptions are a kind of, they're an uncomfortable part of the software engineering pantheon. And a lot of students tend to abuse them, right? The student solution is like, don't catch it, or if you catch it, print out the stack trace and die, or something like that. And the fact is, as professional programmers, we can't be that loose in our way of handling it, just like we have to handle the final rectangle. You know, we're looking for more robust ways of handling things, more robust ways to allow us to compose values that would be more clear to reason about, that will allow us to perform these large pipelines and compose pipelines and be scalable in that sense, and be type safe. We don't have merely distinguished return values, you know, a distinguished long, which we try to pass back and we just ignore it. You know, we pass back a -1, perhaps from our function to indicate we couldn't find a value, but the thing that called us doesn't pay attention and just plows on, uses it like in an array index, and bad things happen. You know, programs crash and people are unhappy. So, ladies and gentlemen, we're looking for ways of having type safety to enforce that we are handling this. And we introduced last time option, and we introduced try, the try component here. Both of them as ways of explicitly and in a type-safe way handling values. And we saw some of the things we could do with them. We saw we could create them, right, with some and none. We could compose them. We could call map on them, FlatMap, filter, in a good way. We could ask if they're empty or defined. We could use this get or else. Who remembers? What does get or else do compared to just get? Anyone tell me? Good. So if it's not defined, if it's none, we can give it a value to use instead. Whereas get, if it's none, bad things happen. It's unhappy and an exception is thrown. We can actually do or else. We can perform a computation if it's empty. So use this value or else return this value, for example. Like perform a computation to do that. And it turns out that when we sum things up, none is just ignored. I didn't emphasize this last year, but it would be germane to some of the examples we're showing here. But, you know, if we were to do something like this, val vec equals vector of sum of 3, sum of 2, none, and sum of 6 or something like that, right? And we were to do vec dot sum. Here you're going to okay, this is interesting. So you're going to have a problem because you can't directly sum up option ints. This vector, it does not know how to directly sum these components. But what we could do is actually map. We could filter it, for example, if they're defined, right? So we could say vec.filter and say is defined, right? And oops, .filter is defined, and then do map this thing .get, right? And then do a sum on that, right? And then sum up the results. Now, what I was saying here, and I'd have to go back and check it, none is ignored by sum. And there is some mechanism, and I'm trying to remember what it was, where you can actually do a sum of quantities and it will simply ignore the values that are none. And I'd have to go back and remember what that is. But there is a way to sort of have it just automatically ignore nones. Okay. So here we can perform computations on things which have some valid, some invalid values in a principled way, have the values clearly marked. And I noted that this is an example of a monad. It's an example of a monad because it observes some monadic axioms, but one of the signs that it might be is that it contains map and FlatMap. And you have the ability to go from values to a monad of that value and back. Okay, so you can take 3 and you can create an option which holds the value sum of 3, and I can perform FlatMap on things. Okay, and it turns out that this composes quite nicely. Okay, so here we are. Okay, now this is interesting, right? Here we have a sequence of values. I should have looked forward to this to explain my earlier comment. So we have a sequence of values here. This could be a vector or what have you. So we don't have to use those particular values, but 2.3, 5.2, and I'll say foo, and 7.2. Okay. Maybe make it 1.2 so it's not obviously ascending. Let's move this out of the way. Okay, here we go. And back to that thing there. We're going to convert each to a specific integer value if possible. And the way in which we're going to do this is we are going to map each of them to an option value, where that option value is either holds an integer or double rather, or it's none. You might think that you could use map here. We're going to say we're going to map each of these to a corresponding value. We're used to thinking of using map to process each element. The problem here, and this is something the book emphasizes in one sentence that I think actually gets to the heart of some thinking about this. What's the problem with using map? So suppose I wanted to use map to map each of these to a sequence of doubles. What's the problem with that? Why won't that work, given my description of what I'm wanting to accomplish? Well, I'll spare you one little bit. I'm going to use a two-double thing on a string here. So I'm going to take in a string, and I'm going to do, I need a try, right? If I just do this dot two double, what will happen? Will it be happy? What will happen? Does this look like it's happy? Sorry? Yeah, foo is not a double. It doesn't know how to parse that double, right? So we can't just naively just say convert each one to a double. Bad things will happen, right? So then we might say, well, okay, well, why don't we try to put a try around this? Remember, try lets us undertake expressions. Remember, we introduced it last time, and I have some examples of it later here. But a try allows us to try things that might or might not work, right? And then once we've got a try, we can convert it to a double, right? Or to an option, rather, an option of double. Okay, so let's try to do this. Okay, so we'll try going to a two double, and it's not able to find try. Okay, fine. Scala.import. I don't know why try isn't import mumble. No, Scala.util. Sorry. Okay, here we go. What's going to happen here? Okay, so we're going to get a list. Okay, that's fine. Of these things, and each of them consists of these items. So here we have a success of each thing, and now we could compute these to option. Right? Here we go, to option, and so now we have a list of each of these items. Right? So we have a list of options. Option is none for values where it didn't work out. And then the option holds a certain defined value, sum of certain values for where it did, right? So that's pretty good. Now, I want to draw a distinction, though. Suppose we were to say we want to flat map this. What would be the difference with flat mapping it? Do you notice there's a difference here? What's going on? Sorry? Yeah, so FlatMap flattens things, okay? And this is a two-level structure. We have a list, that's one monad. And then we have, within the list, another monad, actually, sum, or tries, right? And so, as a result, if we were to process these things, we'd have to process them as an option. If we do FlatMap, it actually reduces it all to one level, which in this case is a list. And none is actually left out, okay, as part of that. So this is part of kind of monadic semantics here. The none is left out, and we get a list of the values, right? And then we can do a nice thing here of simply summing them together, right? Whereas if we had this, could we sum if we had this, could we sum? Why not? It doesn't know how to sum options of doubles. And, you know, we could try to do filter as we did earlier, dot is defined, and then we could do a map of this, you know, map of each thing, dot get, and then we could do a sum. Is defined here, right? We could do that, but it's often much cleaner to be dealing with things in terms of a flat map. And it turns out flat map is key. We saw it, we introduced it last time. We introduced it last time to be able to add things together. Do you remember that? We had val v1. I'm emphasizing this point because we're going to need it again in a coming chapter. You know, sum of 3, and we had val of v2, and this could be none or this, and we actually had v2 last time being none. And I'll declare this as an option of int none. And then we had val v3 being something else. And if we wanted to add them together, do you remember what we had to do? We had to do v1.map. And this gives us the first value. And then we had to say what? Yeah, v2 dot, and it was tempting to say map, but we'll see that isn't quite what we want. It's close, and that will give us our second value if it's, and then we do x plus y, right? The problem is, what's this going to give us? It's going to give us something that's sum of none. That's kind of weird. Let's try it with, what would we have gotten if we did V3 here? What would we have gotten? Sum of 3, which isn't quite what we want. What we actually want is, ladies and gentlemen, FlatMap. Mumble. Sorry. Flat. Sorry.
The outer map?
Sorry, the outer map. What am I doing? The innermost map is flat. Yeah, thank you. Oh, there we go. Yeah. So basically, it turns out when you want to undertake operations, and by the way, if we were to see this, let's generalize this to 3 things. Suppose we want to add all 3 together. How do we do that? So this is this, and then what do we need in here? Okay, I'm going to leave this as map. We're going to need to revisit this, but we need the 3 dot, say map, right? Map-like thing, and then we're going to do what here? X plus Y plus Z, right? Okay, but let's reason this thing through, or let's try this. Okay, let's try doing it all with V3, so we see what we'll get if it. That doesn't look right, right? So what's missing? What do we still have to do here? We want this to be a flat map. It's all but the last, ladies and gentlemen. Why is that? Well, in the book, what the author says is that use map if what you want gives a value to use, kind of in a value directly to use instead of the original value in that monad. So, you know, you're squaring, so you have a value in a monad. It's sum of some number, say, or none. And you're squaring that number. That square is going to always return, if you get a valid number in, 3, say, square of it is going to be valid, 9. So all you're doing is you're sort of computing a valid concrete number and using that. By contrast, FlatMap would be used if an error can occur. You need a monad to be returned. Okay, you actually need, like, let's suppose you're taking a number and you're dividing 50 by it. We saw that last time, actually. So you have a number, maybe you have sum of 0, and the inner thing is doing 50 divided by that thing, okay? In that case, you'd want to use FlatMap because you're going to need to use a try to handle that, and you don't want then a sum of try. You just want a try returned, okay? So FlatMap is used if the computation itself can go wrong or it needs to return different values rather than just you're computing a well-defined value that's then used. So this is in a comment in the last that's chapter on try and option. So here, what's happening is, let's reason this thing through. The only time we get here is what? If we get to this inner place here, what do we know is the case? Well, we know this is some number. It's not none. Well, let me phrase it this other way. Okay, if V1 were none, where would we get to in this whole computation? V1? If V1 were none. Or let's put it this way. If I said V2, where would we get to? Which of these things will be ever executed? It actually won't be executed at all. It'll just return none. It's just short circuits. Because it knows flat map on a none is just going to be none. Okay? Nothing to do at all. No. Similarly, if I had a try that was a failure, if I try to flat map that, it's going to be a failure. Okay. By contrast, suppose that this is legitimate, but this next one, I'm going to change this all. This next one is none. What's going to be executed here then? Yeah, this is going to get an X from the first, right? But V2 is going to return what? None. So this thing, ladies and gentlemen, it has to return be able to return not just a number. It has to be able to return none or some, right? This first thing. So this has to be a flat map. So because this thing could return none. If we get to this point and v3 is none, what is this? Does this ever get executed? No. This thing here, this whole thing v3.map will return what? If v3 is none, it will return none. And so this has to be a flat map because this can return none. Does this guy ever return none? Cannot lie. It can't return none because if we're getting here, we know X is bound, Y is bound, Z is bound, all to legit values. And as a result, this is just going to return a concrete value, like 3 or 10 or 7 or 11, right? And so we don't need actually a flat map. We just need a map. It's returning a concrete value. It's mapping from the original value, which is in this case v3, and it's getting back. So it's v3 is sum of whatever, and it's using a value to sort of use in a sum instead of that, a concrete value, and so that's a map. And this is in general true when we want to combine these things, when we want to sequence a series of operations, like to add these together and so on. We get this combination of flat map, flat map, flat map, and the innermost is a map. The innermost is return a concrete value. Now, there are times where the innermost thing we want to access a website and we want to read something, and that can fail, in which case we want to do something more. Okay, the final thing I want to just leave you with here is this. This little example. So import scala.io.underbar here. And I'm going to create a collection of URLs. Ooh, here we go. Mumble. Val call URL equals. And this is going to be a sequence of URLs. Here we go. HTTP, www.usas.ca, HTTP, www. I don't know, CNN.com, and then HTTP. Let's hope that no one registered this. Fubar. Well, Fubar is probably registered. Maybe someone can check. Fake Fubar fake. Probably that's not registered, right? I hope. Could someone check if Fubar is registered? Fubar.com. Wade is investigating. I saw him type out the right number of characters. There's
a site there.
Yeah. When I was in grad school, I registered myself as Ben Bitdiddle in the phone book. Okay. Okay. So now, ladies and gentlemen, let's map these things. Let's map these. Okay. We're going to map for each one. We're going to try to read the source string associated with them. Okay. So here we go. Whoa. Mumble. It was called cold URL. Okay. If you call it cold URLs, you're better. Call. I call it call. Let me just correct that. I'm gonna switch it back to that. Call URLs, and this is what we want. So we want to take that thing. What am I doing here? What am I doing? Can anyone say? Crudely? For each of those URLs, what am I doing? I am getting the string associated with it. That's the what? Begins with a U, ends with an L. It has an R in the middle. Rull. Lur. LRU, least recently used. Okay. And then we are trying to do what? to actually read from that URL, we're actually reading the text, okay? We're accessing the URL and getting a string back. You notice that? Does anyone recognize this? What is that? Yeah, that's the U of S webpage there, the beginning of it, okay? Okay, and then we're going to do a 2 option. What do you think we'll get back here? What do you think the third item is going to be? Okay, call page options. What do you think the third one is going to be in there? Let's options, right? I think it was this. Yeah. What's that my name for it? Yeah. Call page option strings. Sorry, page option strings. Boom. Okay. If I were to map is defined on this, what do you think I'd find? True, false. Why false? Var fake apparently does not exist. Although any one of you could remedy this. Okay, and then what we could do is we could go and we could, for example, handle them in terms of processing them one by one, right? Another way, though, we could have done with it is we could have said FlatMap here, right? FlatMap here. And this FlatMap would return back what? What is this going to return back? A sequences of strings. How many items is it going to have? 2. That's right. So its size going to be 2. And those are the strings, right? Those are the strings that are valid, right? And then I could simply do, suppose I wanted to, those are the strings. How am I going to add up their size? So suppose I want to add CNN's web page size to U of S's web page size. For any of these legitimate ones, how would I total up their size collectively? This was the size of the collection. Suppose I wanted to add up the size of the web pages, the strings. I could do map each of these to length. I think it's called length. There we are. CNN refused. What's that? Oh, maybe it's HTTPS. Okay, maybe. What is it? Dalhousie is. Okay, I probably could have done that. Here we go. FlatMap. Okay, let's see if Dalhousie's is. Okay, happy. And then we could sum, right? Now the numerics, or we could reduce. Okay, so what we have here is a little pipeline that we could have written all in one line if we had wanted to. But basically, it is involving taking a set of strings, going and accessing the web pages associated with them, filtering out any that are invalid, and rendering them into strings, the ones that are valid into strings, and then mapping them to their lengths and summing them up, right? So we're doing that, and sorry. Right. Okay. So somewhere we are missing the FlatMap. FlatMap. Oh no, there it is. Okay. Okay. Good. There we are. Okay. Sum them up. Happy. Okay. So here we have a pipeline that is robust to problems with these URLs. We deal with the ones that are problematic in a principled way. Here we essentially say, okay, we'll consider their length 0. We'll omit them from the calculation. We handle the errors purely within the pipeline rather than having them propagate up and somehow having to go back and figure out how to restart things. And we compute in terms of a single number. Okay. Obviously, this is a toy example. We have 3 URLs. If you were writing a spider or you were harvesting a set of papers, information from media sites worldwide, this might be hundreds of thousands of different URLs, and you want to be able to robustly handle those errors and accessing them, right? So it provides some general sense of how these pipelines can work. Okay, I will post some other things that will help you folks if you're interested in learning more. Learn how to navigate these, learn more about that for syntax I introduced for handling monads in a nice, transparent way, and provide some extra examples for sort of processing things in this sort of incremental way. But next time, we are wholesaledly going on to a discussion of streams. Okay, and streams will be key for understanding a lot of Spark functionality. Because it has its own sort of mechanisms that emulate many of the features we see in streams. Okay, so that's what we're doing next time, and I'll post the solutions and we'll post these slides. Okay, thank you very much.